Okay, we're ready to move on to our next section in the waves unit, and that's going to be a look at sound in depth. So go ahead and set up your notebook for sound notes. Make sure you put big ideas on the left and tell me mores on the right, and let's get started. So we mentioned this before, but sound waves are a particular type of compressional wave that have to travel through a medium. So they're technically called a mechanical wave. Mechanical waves are waves that must have something to travel through: air, table, water, whatever. They must have molecules to travel through. And as they travel as a compressional wave. You can see here in this diagram a drawing of what the compressional waves or sound waves would look like coming off of a tuning fork here. So you can see as the tuning fork vibrates the molecules, some of the molecules are compressed and some of them are spread out. So here we have the compressions and the rarefactions. So the important thing about sound really is that we hear sounds, and so I want to take a few minutes to go ahead and talk about how our body, how our ears translate those vibrations, those waves, into sounds we can hear. So if you look at this diagram here, you can see that it is a picture of the inside of our ear. It's basically like if you were to cut off the front of your face, as disturbing as that sounds, the front of your face, it's looking at it front on. The first part we would start with is our outer ear here. And the outer ear acts as a funnel. I can even tell right now as I cup my ear that it's focusing the sound waves even better into my ear. So it doesn't really, you could hear without your outer ear, but you probably wouldn't hear as well as those waves wouldn't be focused in. The waves are then focused into your ear canal. It's about a 3-centimeter tube or tunnel that ends at your eardrum. And this here is a depiction of the eardrum, and it is very much like a drum. It's a membrane that's stretched across the back of your ear canal. So when the sound waves hit it, transfers the kinetic energy from the air to that eardrum, and the eardrum starts vibrating. Now right behind the eardrum are these 3 tiny little bones. They're actually nicknamed according to their shape. There's the hammer, the anvil, and the stirrup. And those 3 bones act as little mini amplifiers for the sound wave. So as the eardrum vibrates, it transfers then the kinetic energy to the bones, and they start to vibrate and they amplify that sound wave. Just behind the ear bones is this funny looking organ. It's called the cochlea. Cochlea is super important for your hearing. It is actually full of water or a fluid, and when the sound wave is transferred to the cochlea, as it's vibrating against it, the water inside starts to vibrate. So just like if I was to tap the outside of my water bottle here, the water inside starts to shake. And sticking out inside the water, coming off the inside walls of the cochlea, are these little cells called hair-like cells. And they're not actually hairs, they're just kind of look like hairs or little fingers that are sticking out into the water inside the cochlea. And as the water vibrates, it moves those hair-like cells, and they're the ones that transfer the energy, transfer the sound wave to your auditory nerve. And the auditory nerve is the one that's connected to your brain, where your brain can translate that sound wave into a sound, into what we hear. So just a note on those little hair-like cells, you probably learned about this last year in Miss Blanding's class, and that they're very easily damaged. So long exposure to loud sounds or very sudden loud sounds can do a significant amount of damage to those cells, and there's no going back for that. So you don't have you can't get new ear hair cells, they don't regenerate. They do naturally age and degenerate, so you might know, like with grandma or grandpa that has, not as good a hearing as the younger people. And that's because those ear hair cells do naturally degenerate over time. But if you, while you're younger, spend more time with loud music or loud sounds, even like snow machining and stuff, you are more at risk for having those hearing problems. So these pictures here, I want to look at just this one in particular. And this is an electron scanning microscope photograph of the inside of your cochlea. And these are the little ear hair cells. Some of these you can see here are very nice and healthy and straight, where some of these back here have sort of degenerated and are obviously damaged. So you can see how that might look inside your ear. The next few slides, what we're going to look at are some of the properties of waves as they relate to sound waves. So we've already talked about some of these properties, but now we're going to apply them to what they look like in a sound wave. And that first property is amplitude. Amplitude, we talked about, is how big or small the wave is. So a large amplitude wave is really big, small amplitude wave is really small. The cool thing is that a large amplitude wave or a small amplitude wave sounds different to our ears, and we hear that as loudness. So the louder the wave, the louder the sound, the higher the amplitude. The lower the sound, the lower the amplitude. We measure loudness or amplitude for a sound wave in a unit called decibels. You've probably heard of that. And we do abbreviate that dB here. So you'll see that. I'm going to turn on my pen here, if I can. Maybe not. You can see this dB unit here. So we got it there. This chart is just looking at some familiar sounds and relating them to the decibel level, just to give you an idea of what a decibel level is. So here we've got, your average home, normal conversation around 50, 60 decibels. Start to get up here, a ambulance siren and stuff at 120 decibels. I put some information over here, like a snow machine, and obviously it varies based on age and engine type, but about 100 decibels. So I want to point out here that it's around 85 decibels where is the recommended threshold for exposure. So any decibels above 85 you shouldn't experience for a long period of time. So really good motivation to wear hearing protection while you're snow machining. You get death of hearing tissue at about 180 decibels, though even down around 130, 140 can cause damage for even short exposures. The next one is speed. Often you'll hear about this, speed of sound. And of course the speed of sound is just how fast a sound wave is traveling. The one thing I want to point out here is that it actually depends on what it's traveling through and the temperature. So a couple things that come up is that sound actually travels faster through warm air or warm things. So if you have two places, like say Alaska and Hawaii, the sound waves actually travel faster in Hawaii than they do in Alaska. It's warmer. They also travel faster through solids and liquids than they do than gases. So sound travels faster through my desk than it does through the air. This chart here is just some representations of some different speeds of sound through different materials. This is what we generally talk about. If someone said, what's the speed of sound? It's usually given through air at 20 degrees Celsius and is 343 meters per second. You are going to want to write that down in your notes. I'll be asking you that again. The next one is frequency, and we did mention this in class, that the frequency of a sound wave, so again how often the wave occurs, is heard as a change in pitch. So when we hear a high frequency sound, it sounds high pitched to our ears. When we hear a low frequency sound, it sounds low pitched to our ears. So here, this chart I like is giving some hearing ranges for different critters. Here's humans' hearing range. So we can hear sounds as low as 20 hertz and as high as 20,000 hertz. And of course this varies by age and person, but it's general. Elephants, you'll notice, are lower. They hear very low frequency waves, so much lower than us, and they also don't hear high frequencies like we do. And then you look down here to things like bats and dolphins, and they hear extraordinarily high frequency waves. So pretty cool information there. The next thing I want to talk about is a particular phenomena that occurs with sound. It's called the Doppler effect. You may have heard of this before, but certainly everybody has actually heard the Doppler effect before. And this is the sound you get when you are standing, say, on a sidewalk, and maybe a police car or an ambulance or something drives by, and you hear, right? You hear that change in frequency, change in pitch as it drives by. And really what's happening is this thing called the Doppler effect, where because the car is moving and making sound, it's moving into its sound waves. So it's bunching the sound waves up in front of it, causing us to hear a higher pitch. And then behind it, as it's going away from us, it's moving away from its own sound wave, we hear a lower pitch. So it kind of looks like this little animation here. So I do have a short video for you to watch here. I'm going to include it as a separate link. So if you could go ahead and pause the video now and watch the Doppler effect video and then come back to the video. The last thing I want to talk to you about is another behavior of waves, in particular sound waves, and that's when a sound wave is reflected. A sound wave is reflected when it hits a surface and bounces off. And this is called an echo. So if you've heard, hello, 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 that's a reflected sound wave. Excuse me. Sorry about that. So an echo is a reflected sound wave. And repeated echoes are called reverberation. So the sound reverberates off of a wall or something. The last thing is that there are animals, of course, that use echoes, use reflected sound waves in order to hunt or talk to each other or so on. Things like bats and whales use echolocation. So they're sending out a sound wave, and that sound wave is being reflected off of something and coming back to them, allows them to orient themselves in their surroundings. Also, we use it in things called sonar. Sonar is a human use of echolocation, as well as ultrasounds. Ultrasounds, like maybe a pregnant woman gets an ultrasound to look at the baby. So some common uses of sound waves. This is just a little animation that shows a bat sending out a sound wave, the sound wave echoing off or reflecting, and them being able to hunt for insects. So again, make sure you check for that Doppler video and make sure your notes are complete.